Right, so just going for the starter then. So firstly, question number 1, restricting the domain. So remember, to be a function, it has to be defined for all values in the domain. Now, the square root of x minus 4, of course, there'll be many values of x that you would put in that you get an undefined value. So I'm going to need to put in something that is, well, firstly, I'll define x as any real number. But then what I'll do is say that x has to be greater than or equal to 4. And that's because I can't square root a negative number and get a real solution. So if I put in something like 3, then I'll be doing 3 take away 4, which could be -1, which is undefined. Okay, well, it's not going to give me a real solution. So I need to make sure this value of x I put in is going to be 4 or greater. The second one then, so y is x plus 2 all squared plus y minus 3 all squared equals 9, not a function. Now this is a equation of a circle, so just a little reminder on that. Your centre of that circle will be -2, 3, and this will have a radius of 3 as well, okay, square root of 9. So because it's a circle, it's a many-to-many function. Sorry, many-to-many mapping. Okay, so it's many-to-many mapping, so not a function. So both those questions kind of just going over the 2 reasons to be a function. The first one is that it's got to be defined for all values in the domain. So, for example, that first one, it's a function as long as we restrict that domain. And the second one is not a function because functions are only one-to-one mappings or many-to-one mappings. Okay, one-to-many or many-to-many are not functions. And then finally, for 3, we might just want to draw a sketch. So this is already in complete square form for us. So we could just do a little sketch like this. And we've got our turning point there at 4 minus 3. Now my domain is restricted between 3 and 8. So 3 might be somewhere about here, and then 8 somewhere up here. Okay, so we can see that 4 minus 3, that's going to be the smallest value. Okay, so the lowest value there is going to be -3. So that's at the bottom of my range. And then the largest value between x equals 3 and x equals 8. But when I put in x equals 8, so I put that in the equation there, I'm going to get 13. Now, what I saw on a few of your responses from the questions yesterday is some people saying, well, I can't put 8 in because it's less than, so I'm just going to put 7 in. So I think what you're doing there is you're thinking about when we do binomial and it's discrete, so we can't have 8. But here, we can essentially have 7.99999. Now, what that means is we're pretty much going up to the 8, but we get around that anyway because we just keep that less than sign consistent. Okay, so that would be your range. If you've got any questions, let me know. If not, we're going to carry on with our examples today. So there's not really much new stuff in terms of theory, but these are some quite harder examples than what we did yesterday. The first example we're going to do. Oh, one thing I should have said yesterday. Apologies that we have jumped a few pages in the booklet. We are going to come back and do the transformations, but some of those transformation questions needed this range and domain work that we're doing. So we are going to come back to that. Just want to make that clear. So the first question, state the domain and range of the function f of x equals 2 minus 3 over x squared. Now, what's going to be helpful to do first is to sketch this function. And I know it might be a little bit tricky to sketch this, so I'm going to sketch this in a few stages, just so you can see how it's going to look. So I'm going to draw 3 sketches before I actually show you what the final one looks like. Or 2 sketches, and then I'll show you the final one. Firstly, what I'm going to do is I'm just going to sketch 3 over x squared. Okay, so this is what 3 over x squared would look like. So if it was just 3 over x squared, the graph would look like this. If we make it negative 3 over x squared, we reflect in the x-axis. So our graph would look like this. But then we're going to add 2 to this. So our final sketch let's make that look a little bit more realistic. Our final sketch would look like this. Okay, it's going to have an asymptote when y is 2, and it's never going to go higher than that 2. Okay, so just think about why that is. 3 over x squared is always going to be positive because you square x, so it's always going to be 0 or greater. But then because you're timesing it by a negative, it's going to make it always negative. So you're always doing 2 plus some negative number here. So from this sketch, this will help us determine the domain and the range. So firstly, my domain. So we didn't do much of this yesterday in terms of actually stating what the domain is. So my domain, I'm going to say that x is any real number, but there is one exception, of course, and that's that I can't put in x equals 0. As you can see on the sketch to the left here, I've got this asymptote at x equals 0. That means that I can't put x in this, otherwise it won't be a function. Okay, this is many to one, so it's met that criteria, but I have to make sure that I say x cannot be 0, otherwise it won't be defined for all values, and therefore it won't be a function. The range, well, that's just going to be f of x is less than 2. If you look at the sketch there, you can see you've got an asymptote there where y equals 2. Now remember, this graph will never quite touch that asymptote. It'll get very close to it, but it'll never quite touch it, which is why I need to make sure I've got the less than sign there. Okay, that is really important. If you've got any questions, pop them in the chat. If not, we will move on to example 4. So we've got another function now, and this is a quadratic. Probably a little bit easier than the first one in terms of the sketch. So in terms of sketching this, I could just simply factorize this, which is just x minus 5, x plus 1. What that means is my roots are at x equals 5 and x equals -1. So let's just sketch that now. So I've got root there, -1 and 5, and your y-intercept, so putting x is 0, your y-intercept is going to be there at -5. So my domain for a quadratic, there's no value of x that I can't put in. Okay, I can put anything from -infinity to +infinity there. So x is just defined for all real numbers. Okay, so I just put my domain is x belongs to the set of real numbers. I can just leave it as that. B says complete the square and hence find the range. Yeah, again, something that I picked up from the questions did yesterday. That y-intercept is not your lower limit of the range. Occasionally, your y-intercept is the turning point as well, but this is the turning point where I put the cross there. We need to find that lowest value, because with a quadratic, if it's a positive quadratic, all your y values that it outputs or your f of x values that it outputs, it's just going to be that value or greater. You'll never get a number lower than this lowest point here. So we just complete the square. It shouldn't be anything too difficult, hopefully. So your x squared minus 4x just becomes this x minus 2 all squared minus 4. And then we just need to make sure we include that -5. -4, take away 5 is just -9. So the minimum value this can be is -9. Okay, you don't necessarily need to label the turning point here, but it might help. So your lowest value here is 2 minus 9. So what this means for my range, is the range is just simply f of x has to be greater than or equal to -9. Okay, greater than or equal to here because 2 is in my domain, so I can put in x equals 2 and that will give me -9, but that's the lowest value. F of x is only ever going to be -9 or greater than that. Okay, you'll never be able to make a -10 or a -11. There's no value of x that you could input there and get -10, -11. For all the numbers, or all the real numbers that you can put in to the quadratic, you will get -9 or greater. You'll never get anything below that. So they're kind of sort of medium difficulty questions. So a little bit of an expansion on what we were doing yesterday. Now it's time to get into the slightly harder ones. Okay, so these examples 5 and 6, and also the past paper question at the end. So getting you used to, in the exam, kind of those kind of curveballs they like to throw at you, some harder style questions. Especially this example 5, getting used to questions where they give you missing constants. I mean, you already saw one of those examples earlier in the week with the modulus question where you had to give your root in terms of a. So they do like doing this, especially in new spec where they know there's a lot of things that you can do in your calculator. What we're going to do, we've got a quadratic here. It might not look like a quadratic, but remember you still got an x squared term, you've got a x term, and then you've got a constant term. So it's still in that form, ax squared plus bx plus c. What we're going to do is find this constant p. Okay, so p could be, for example, 1, and that would mean 5x squared plus 10x plus 3, for example, would be your quadratic. But we're going to find out what that constant p is a little bit. Sorry, we're just going to leave it in terms of p, for example. So I still do the normal thing I would do to find my lowest value. Okay, so with example 4, we complete the square, so we can find the turning point. It's still what we're going to do here, but we're just going to do it in terms of p. That's the only difference. So quite a tricky one to complete the square on. But what we have to do when we've got a coefficient of x squared that's not 1 is we need to take that outside of a bracket. So there's a 5 in front of the x squared, so take that out, and we'd have x squared plus 2px in the bracket there. Don't forget you've got this 3p squared as well. Okay, so just look at those first two terms, take the 5 out. Some people like to take the 5 out of the 3p squared as well. You can do that. I don't like doing that, but I know some of you do that. It's not wrong. It just can lead to more mistakes, in my opinion. But if you prefer doing it that way, you can do it that way. Now what I'm going to do is just focus on this bit in the brackets here. So I'm going to complete the square on this x squared plus 2px here. So I just write x plus p because p is half the coefficient of x. Okay, so you've got 2p there, you've got p there. So that becomes x plus p squared. When I expand that bracket out, I get my x squared, I get my 2px, but what I also get is an unwanted p squared. So to compensate for that, take away a p squared. And then don't forget, outside these square brackets, I've got this 3p squared. Okay. Again, if you prefer to kind of just take the 5 out the whole thing, then obviously that will also be here in your square bracket as well. But it wouldn't be 3p, it'd be 3 over 5p squared. Then it's just time to tie this up a bit. So I'm going to expand those square brackets out to get 5 times x plus p all squared minus 5p squared plus 3p squared. Okay, that doesn't get times by the 5. And that just leaves me with 5x plus p all squared minus 2p squared. So if you struggle with those harder completing the square questions, have another look at them again. Later today, I'm going to post something out about how you can find some more resources, basically some free textbooks and free revision resources to use if you want to do some more questions. So stay tuned for that a little bit later today. So in terms of my range, when I complete the square, this value here is my lowest value. Okay, if I wanted the turning point would be minus p minus 2p squared. Okay, when you put in minus p, that sets that bracket to 0, and then you get left with the minus 2p squared. Okay, that's as low as it will be able to go. So your range would say g of x is greater than or equal to minus 2p squared. If you wanted to sketch this, it would look something like this. Okay, with that being your turning point. Okay, and it's only ever going to be greater than that turning point. I don't necessarily know that p is a positive constant, by the way. This is just a hypothetical sketch, but it might look something like that. Okay, we know it's definitely a positive quadratic though, at least. Again, any questions, let me know. We've got a couple more examples to do, and then it's over to you. So example 6, determine the domain of f of x equals square root of x plus 3 over x minus 7. Because we're using that function notation, it's a function, so it must be valid for all values of x that we put in. So we need to make sure that all values of x in our domain will not lead to anything that is undefined. So I'm just going to start with the numerator, and then I'm going to get on to the denominator. So if I look at my numerator, it's a little bit like what we did in the starter. Where is the square root of x plus 3 valid? Well, this is valid as long as you've got 0 or greater inside that square root. Okay, so square root of x plus 3 is valid if x is greater than or equal to minus 3. Remember, greater than or equal to, we can do the square root of 0. I know when I've given this question out in the past, some people just put x is greater than minus 3. We can have greater than or equal to minus 3 because you can square root 0. It's just that you can't square root a negative number and get a real solution. So x has to be greater than or equal to minus 3. Okay, anything greater than that is absolutely fine. So 5, 10, a million is all fine to put in here. Nothing that's less than minus 3. Then we look at the denominator. So the denominator is valid as long as it doesn't equal 0. Okay, so as long as x minus 7 doesn't equal 0, so therefore x cannot be equal to 7. Okay, if I put 7 in there, then you get 0 on your denominator, and then it would be undefined. So what this means is my domain, firstly, it's important I say x can be any real number, because I need to make sure that I'm saying that, you know, I can put in numbers such as 3.28, I can put in 3.36828. Okay, all of those numbers, rather than list them all, which would take a very long time, I just put that x can be any real number, but then I put the restriction that x has to be greater than or equal to minus 3, and x cannot equal 7. Got one more example to do. Let us know if you've got any questions. And then we'll get into this final example. So a past paper question. And the questions that you're going to practice today are from various past papers. They can be, pardon the pun, quite a range of different questions for range and domain, and they come up in lots of like places, not just kind of maybe these sort of topics that we're doing here. So it could come up in other things as well. So really, you've just got to practice a whole variety of different questions when you do this. So here's our past paper question then. Sorry if it's a little bit blurry on your screens at the moment. Hopefully you've got your booklet in front of you to see a bit clearer if you can't see it clearly here. So we've got a function x which is defined as, I'll write it a bit bigger if you can't see it, k times x squared plus 4x, and k is a positive constant, and we've got a diagram here of f of x. The first thing we're going to do is find the range of f in terms of k. So yeah, again, completing the square is going to be my best friend here. So I'm just going to complete the square inside that bracket. So x squared plus 4x is just simply x plus 2 all squared, but if I expand that out, I get a positive 4 that I wouldn't want. So then I expand that bracket out. So just times everything through by k. And then hopefully we can see, remember k is just a constant here, so it could be 2, 3, 5, 6, etc. So when I've done this, I've got a turning point here when x is minus 2. Y will just be minus 4k. So the minimum value is minus 4k. Yeah, and that's just because when I put in x equals minus 2, that makes that bracket equal 0. Any other number you put in, you're squaring it, so it's always going to be positive. So 0 is the lowest number you can get out of that bracket when you square it. So the minimum value, therefore, must be minus 4k. So your range, and we just do this in terms of k, we're going to find k in part 3. Can't remember why we took out part 1 here. So f of x is just greater than or equal to minus 4k. So then we get into a slightly harder question now. So it's given that there are 3 distinct values of x which satisfy the equation modulus of f of x equals 20. Find the value of k and determine exactly the 3 values which satisfy the equation in this case. Okay, exactly means we're going to have to give this in its exact form. If I see the word exactly or exact value in a question, a lot of the time that makes me think it's either going to be a fraction, it's going to be a surd, it could be a natural log, it could be something in terms of e. So just bear that in mind. A key word like exact or exactly, that is kind of hinting that it's probably not going to be an integer. All solutions aren't going to be integers here. So part 3, we're looking at the modulus of f of x equals 20. So this graph we've got here is just f of x. If I want to draw the modulus of f of x, I'm just going to draw it on here. I just reflect my negative bit here. So in terms of key points here, that minus 2 minus 4k, what was my minimum value? It now becomes a minus 2 positive 4k. Now the question says there are 3 distinct solutions. So what this means for x for modulus of x equals 20. So what I need to do is draw a line of where it's going to be 20. But the fact is, if I just have my ruler here, you can see if this is where I say 20 is, then it'd only be crossing twice. Okay, that means there's only 2 solutions. If I put my ruler further down here, I can see that it's crossing 1, 2, 3, 4 times. So that's more solutions than we need. So if there's only 3 solutions, that means it has to cross, it has to just touch at that turning point. So that's my line of y equals 20. So I've got 3 solutions there. I've got these 2 solutions on the sort of these parts of the quadratic, and then that turning point there is going to be my 3rd solution. Okay, but it has to just touch there, because if it was lower than before, if that line was higher, then there'd be 2 solutions. So I know that 4k equals 20, and therefore k equals 5. So, and remember that 4k just comes from the fact that I've reflected this negative part of the quadratic because I'm finding the modulus of it. So it just becomes a 4k there. So I know that at that point there, that has a value of 4k, which has to equal 20 for there to be 3 solutions. So k simply is just going to be 5. Now that I know that k is 5, it will help me find the other solution. So firstly, the first solution we can just see is right there for x. Okay, so this first solution is going to be x minus 2. Okay, so when because k is 5 there, we can just see that first solution there is minus 2. Okay, that's just a turning point. And then we want to find our other solutions. So what we're going to do to find the other solutions is sub in k equals 5 into f of x. Now we know what it is. So we look at f of x and we can just put in that 5 x squared plus 4x. And we're just going to expand it out as so. And I'm looking at where f of x equals 20. So I don't just set this to 0 because I'm not trying to find the roots here. I'm trying to find out where f of x equals 20. So I'm going to set f of x to be 20. Now, I know this is modulus, but if you look at these other two solutions, so the ones that I'm going to highlight in green here, okay, neither of these two solutions have been reflected. So I don't need to multiply f of x by -1. Okay, both of these solutions, regardless of this whether it's modulus or not, both of these solutions were above the x-axis. Both of these were positive values of y before anyway, so I don't need to multiply through by -1. So then what I do is I just rearrange this quadratic and I solve it. So I can just simply use my calculator here. And I've mentioned before, it did say exact. So I'm just going to leave it in terms of a third. So in terms of your solution, k is 5. Remember, we were asked to find k. And x is going to be -2. That's the first one we found there, just highlighted in yellow. And then also we have -2 plus or minus 2 root 2. So I've got 3 solutions in total there, and that's what I was required to do.